Greetings! Welcome to Electronics 2. This is lecture number 17 and I am Razavi. Today we will begin a new topic for our studies that is very interesting and very exciting. And that is the concept of frequency response. We will see what we mean by frequency response, what is our objective in studying circuits in terms of their frequency response, and why exactly we want to do that. And then to get there, we have to review some basic concepts from circuit theory to prepare us for the proper analysis of frequency response of circuits. So that's how we will spend our time today. Now, the objective of frequency response is actually quite simple. Here's what we want to do. So let's change the color to maybe this color here. So our objective is as follows. We want to determine the speed limitations of circuits. Okay, so we have seen many different types of circuit topology so far in Electronics 1 and Electronics 2. We have calculated their voltage gains, maybe sometimes the input and output impedances and other properties. But we have never asked ourselves, how fast can these circuits run? Can I take an amplifier like a common source stage and run it at an input frequency of 100 megahertz, 1 gigahertz, 10 gigahertz, 100 gigahertz? What exactly happens if I apply a higher and higher frequency to the input of some of these circuits? Does the circuit still act as we want it? Does it still amplify or not, right? So we would expect that there would be some limitations somewhere. Okay, so by speed limitation, what we really mean is what does the circuit do as we give it higher frequencies? And so here's an example that I can show you. Maybe I can do it in the time domain, which is a little easier to see. So let's say I have bought this amplifier and it has some gain and other characteristics. And then I come along and in the time domain, I give it a pulse. Okay, so this pulse goes from some amount, say 0 to V1. Okay, so this is the input signal going to this amplifier. Now, what does the output of the amplifier do? Well, if the output of the amplifier does this, so it follows the input pretty well, so it jumps up pretty well, and then jumps down pretty well, then that's a good amplifier, right? So V out has this type of characteristic. Now, it may start from 0 or some amount, and then it goes up to this value. Maybe we have amplified the signal. So if this change is, let's say, 100 millivolts, this change might be 200 millivolts. Okay? All right, so that's a pretty good amplifier because the output responds quickly to the input changes. On the other hand, let's change the color to red. If the response looks like this, if the output says, well, actually, I cannot change so fast, I will need some time to change. And by the time it's over here, it still hasn't had a chance to reach its final value. And then the input wants to jump down. So the output also has to go like this. Okay, so that would be an example of a slow amplifier. It is not capable of responding quickly to the changes that are happening at the input. So this is what you would call a slow amplifier. And this is what you would call a fast amplifier. So our objective in the study of frequency response is determine quantitatively, eventually at the beginning qualitatively and then eventually quantitatively whether the circuit is as good as this or as bad as this, right? So we want to understand the limitations that the circuit imposes. All right. Okay, so that's the objective. Now, why exactly do we want to do this? So let's talk about the why. Well, high-speed circuits are everywhere. So we can just look around and look at all the circuits that we find in our devices today. And the speeds are quite high. They are very impressive in terms of what they do. Okay, so for example, we have Wi-Fi, which operates around 2.4 gigahertz. 2.4 gigahertz, so that's 2.4 billion hertz. Also at 5 gigahertz. Then we have Bluetooth. Bluetooth operates around 2.4 gigahertz also. 2.4 gigahertz. Then we have GPS. GPS operates around 1.5 gigahertz. Then we have radars. In your car today, you may have one or two radars. These are called automotive radars. And automotive radars operate around 26 gigahertz. And also the newer generation is going towards 75 gigahertz. Okay. And then there are many other examples. For example, microprocessors that are used in your computing devices, in your laptop, a desktop, even mobile device, right? These microprocessors operate very fast these days, on the order of 4 to 5 gigahertz. 4 to 5 gigahertz. So we see that we have lots of circuits that run at high speeds, and obviously to be able to run a given circuit at such speeds, we have to design it properly. We will see that there are many limitations that come into the picture, so we can't just go ahead and put some devices together and hope that it will work at 75 gigahertz, right? So we have to have enough understanding of what exactly limits the speed, limits the maximum frequency that the circuit can take and amplify or process before we can optimize the circuit for the desired speed. All right, okay, so that's the motivation for studying these things. Now, let me just give an example, something that is somewhat familiar in terms of this type of behavior, right? So have you seen anything like this in the past? Yes, if you take a simple resistor and a capacitor network like this, and we give it a, for example, step, so V in, and we look at this output, V out. So if V in is a step, so 0 to V1 as a function of time, what does V out do? Well, we remember that V out is an exponential function in this case, right? So if V in is a step, V out would be, it wants to reach a value of V1, but with an exponential behavior, exp minus t over tau. Tau is what they call the time constant, and tau is given by the product of this R and C, R1, C1. So V out will have an exponential behavior, also trying to reach V1, but with the time constant of tau as a function of time. Okay, so that's something we've seen in basic circuit theory or even physics, and we know that V out cannot respond quickly to the input change if this time constant is excessively long, right? So to improve the speed of the circuit, we must minimize the time constant, R1 times C1. So to improve the speed, we must minimize R1, C1. Okay, so now how that is possible and to what extent it is possible, we will have to see. But we know that that's the only variable under our control, right? R1, C1 product has to be minimized. Okay, so that's what happens here. All right. So what we studied here is called a time domain analysis, right? Because I apply something to the time domain, I looked at the output in the time domain, and I figured out what's going on. So let me change the color here and say this is time domain analysis of this simple RC circuit. Okay, now I would like to talk a little about the frequency domain analysis as well. So let's talk about frequency domain analysis. So this is part B, frequency domain analysis. All right, so we want to understand what this is, why we might do this, why we might do this, are they related, all that stuff. Okay, so by frequency domain analysis, what we really mean is something like this. So this analysis tries to formulates the response to sinusoidal inputs. Sinusoidal means sine of omega t or cosine of omega t, right? That sort of thing. Okay, so these would be something of this nature, sine of omega t or cosine of omega t. Omega is the frequency of the signal. Now, pictorially, what this means is this. Suppose I have that circuit, and what I do is I try different cases. So R1, C1, I try an input sinusoid like this, and then I increase the frequency. So something like this, and then something like this. Okay, 3 different cases, for example, right? So 1, 2, 3. And I'm wondering what the circuit does. If I have a sinusoid at this frequency, well, maybe the output sinusoid has about the same amplitude as the input. So this swing is the same as that. So maybe the output has this. But how about here? This is a higher frequency. Will the output still track this, follow this faithfully? Will the output be similar to this? Well, maybe not. Maybe the output will be attenuated. So maybe instead of getting all of this amplitude, we'll have a smaller amplitude. And then how about this case? Maybe even a smaller amplitude than that. So maybe it will be like this. So that's what we want to study. We want to be able to write equations and perform analyses such that at the end we can determine how a given circuit, this is very simple, a more complex circuit, how a given circuit responds to these different scenarios, right? Maybe as the frequency increases, the signal experiences attenuation. So by the time it goes from the input to the output, it's actually smaller, as you can see, right? So there are different possibilities, but that's something that we would like to understand. So that's what we really mean by frequency response or frequency domain analysis. Okay? And we just have to figure out how exactly this will be done mathematically, right? So that's what we will study today. Okay. All right. So now why is it that I want to go from time domain analysis to frequency domain analysis, right? Isn't this sufficient? For any circuit, we can analyze this, right? We can analyze the time domain. We end up with some differential equations or something. So why bother with this? And that's true. If we had never invented the concept of frequency domain analysis, it would have been okay. But the understanding circuits and systems in the frequency domain gives us additional insights, additional understanding of what the system does. And that's very valuable. Okay, so let's go to the next slide and see what we can do here. All right, so what I wanted to do is the following. So let's change the color here. So let me just talk a little about why we want to perform frequency response. Okay? All right. Well, for that very simple RC circuit, it seems that the time domain analysis is fine. There's no particular problem. But what if I have something like this? Okay, so you can think of this as V in and this as V out, etc. Right? Now this is a little more complicated, right? So yes, we could still write a differential equation for this circuit, but it would be of second order. So now we have to solve a second order differential equation, which is okay, we can do that, but it's more work. But now let's look at some other circuits that we have seen recently. So here's a cascode amplifier. Okay, so let's put a PMOS here also, another PMOS. This is the cascode that we saw before, right? So V in, V out. Okay, so if we are interested in the frequency response of the circuit, we will see that we have to include lots of capacitances, and there are lots of capacitances here that we haven't looked at yet. So those capacitances will look like this. There's a capacitance here, there's a capacitance here, there's one here, one here, one here, one here, and many more. Okay, I'm just showing you some. So exactly what, how would we write the differential equation here, right? It will be a very high order, very complicated differential equation. So that's why we are thinking that if we perform the analysis in the frequency domain, we can avoid differential equations and maybe the results are easier to interpret, to solve. And that's one of the beauties of a frequency domain analysis. Okay, so as we will see later, the use of frequency domain to analyze a circuit like this is much easier than the use of time domain. Okay, so let's take a look at some circuit theory concepts. To be able to get to this point, we have to work very hard and we have to work a lot. We will need to build a great deal of foundation before we are ready to attack a circuit like this. Okay, so we have to be patient. We're going to go step by step. Starting with some of the circuit theory that we've seen before, we have learned as freshmen or sophomore in college, and then gradually build up towards a point where we can analyze the behavior of a circuit like this. Okay, so we'll start with circuit theory concepts. My objective is not to teach you circuit theory. That's not what this course is about. You have learned that before. I just wanted to show you a few points that we need in this study. Okay, so number one. Number one is, let me try to start with a capacitor. So we start with a capacitor for now, because that turns out to be the most troublesome component in our circuits. And we give it a voltage and measure a current. This is C1. All right, so I'm going to create a, let me erase this part. I will create a time domain column and a frequency domain column. Time domain and the frequency domain. We want to analyze these in these different domains and gradually make them more complex circuits. All right, in the time domain, what do we know about the capacitor? Well, we know that the current flowing through the capacitor is equal to the capacitor value times the derivative of the voltage across the capacitor. So that's all we know. I1 is equal to C1 dV1 over dt. Okay? All right. In the frequency domain, what do we know? In the frequency domain, what we know is that the current is equal to C1 S V1. In other words, we know that V1 over I1 is equal to 1 over C1 S. And that's what we call the impedance of the capacitor. So that's the impedance. It's similar to resistance, except that it applies to reactive devices such as capacitors and inductors, right? Impedance. In that sense, it satisfies Ohm's law because we can say V over I is some linear impedance. Okay, so that's what we have learned from basic circuit theory. In the frequency domain, we can characterize the capacitor by this type of impedance. All right, well, let's go one step further. So we go to 2 and add a resistor here. So R1, C1, and we are still interested in this voltage and this current, okay? All right, so what can I say here? Well, I can say that the voltage drop across this resistor is I1 times R1. So that's I1 times R1. So I can say that V1, I'm writing a KVL. This voltage is equal to this voltage plus this voltage, right? Okay, this voltage is R1 times I1 or I1 times R1. And then this voltage is the voltage across the capacitor. What I have is I1. I1 is flowing through the capacitor. If I have the current and I need a voltage, what do? I have the current, I need a voltage. I have to integrate. So it would be 1 over C1 integral of I1 dt. So that is the integral differential equation that describes the behavior of the circuit. In the frequency domain, what can I say? The frequency domain, I can say that V1 is equal to I1, R1 doesn't change. So R1, I1, that's still Ohm's law. But then for the capacitor, what we had was something like this, right? So the voltage across the capacitor is given by the current times the impedance. So I1 divided by C1S, right? For the resistor, it's the current times the resistance. For the capacitor, is the current times the impedance. So that's what we have. So the key point here is that as we go from the time domain to frequency domain, we go from differential equation or integral differential equations to algebraic equations. So these equations are much easier to solve than these equations, right? And that's why in many cases this is preferable to the time domain analysis. All right, let's go one step further. So this is number 2, number 3. So suppose I have the same circuit. So R1, C1, and this time let's call this V in. okay, V in, and we are interested in this output. So we call this V out. So I need to express this whole thing in the time domain. So I'm looking for some sort of differential equation that relates V out to V in and then R1 and C1. Now we should be able to do that, right? That's not that hard. Okay, so how do we do that? Well, if this voltage is called V out, how much is the current through C1? So I'll change the color to red. This current is given by this equation. So that current is C1 dV out over dt. That current now flows through R1, right? Because it has nowhere else to go. It cannot go from here. It has to go from here. So this current flows through R1, generating a voltage, which is, according to Ohm's law, R1 times the current. So it's R1 times this current. So what I have is R1 C1 dV out over dt. This is the voltage drop across R1. Okay, now we can write a KVL. This voltage is equal to this voltage plus this voltage. So V in is equal to R1 C1 dV out over dt plus V out. So this plus V out is equal to V in. So that is the differential equation governing the behavior of the circuit in the time domain. Okay, how about the frequency domain? What do I do? So let's write the frequency domain behavior here. So in the frequency domain, again, I am dealing with impedances and resistances. So if I think about this in the frequency domain, I can say, well, there's a resistance here. You can call it impedance also, from here to here. And there's another impedance from here to here. Right? So we have some two-terminal impedance from here to here, some two-terminal impedance from here to ground. And that reminds us of a voltage divider, right? So this is a voltage divider, and it's a more general voltage divider than if we use only resistors to divide the voltage. So if this is a voltage divider, I can say that the output voltage is equal to this impedance divided by this plus this multiplied by the input. So in the frequency domain, I can say it's a voltage divider, and what we have is V out is equal to this impedance divided by this impedance plus this impedance. So 1 over C1S, that's the impedance of a capacitor, right? Divided by 1 over C1S plus R1 times V in. So we have subjected V in to an attenuator. This is an attenuator, right? So the result is very simple, 1 over R1 C1S plus 1 times V in. So that's what we call V out. You've seen this in basic circuit theory, and this is what we call the transfer function of the circuit, right? So this is called the transfer function. Transfer function, because it tells us how the input transfers to the output, right? That's the transfer function. So sometimes we call it H of S, right? H of S, that's the transfer function of the circuit. Okay, so again, you see the contrast between time domain and frequency domain analyses, right? So here we always end up with differential equation. Here we always end up with some sort of algebraic equation, maybe a rational factor, rational transfer function or something like that. So generally handling these things is a lot easier than handling these. All right, so that is what we have for these different circuits. Let's talk a little about, all right, I have covered all of these. Okay, the next concept that I want to introduce is this concept number 4. So S is generally a complex frequency. Okay, this S that appeared everywhere here. If you remember, this arises because we assume that the input has something like e to the st in it, and then at the end we get this. So anyway, S is generally complex. All right, but we can assume S is just an imaginary number, j omega, so it doesn't have a real part, it's just imaginary, if the signals of interest, so the input signal, the output signal, all the signals are sinusoids. Okay, so again, sine and cosine as we saw on the previous page. All right, so that's an important concept that we utilize all the time. So again, for example, let's go back here. This transfer function that we obtained, right? So we had h of s is equal to 1 over r1 c1 s plus 1. So it's for any s, right? But then we decide that, okay, for some particular analysis, we will assume that the input going to the circuit is just a simple sinusoid, right? Like what I showed you on the previous page. So if it's a simple sinusoid, I can say, so if V in is a sinusoid, then S is equal to j omega, and that means that h of j omega is equal to 1 over r1 c1 j omega plus 1. Okay, so now you're asking why do we go through this trouble? This doesn't seem particularly simpler than this, right? We just replace S with j omega. But we will see as we go along that this actually becomes much more useful. All right, I need to talk about one more concept. This is actually more from complex number theory than basic circuits, but anyway. So a complex number, a plus jb, this is a complex number, right? This is the real part, this is the imaginary part. Can be represented in polar form. So let me show you. Suppose that we have a Cartesian representation of this. So this is the imaginary axis, this is the real axis, right? Okay, so this says the real part is A, the imaginary part is B, so the point of interest is here. So that's the Cartesian representation. I can turn it into a polar representation. Polar representation means we have a line from here to here. We are interested in the length of this line and this angle. So the length of that line is called the magnitude of the complex number. So magnitude means from here to here, this length. And how much is that? Well, that's just square root of a squared plus b squared. So square root of a squared plus b squared. That's the magnitude. And then there's an angle here, right? So we call that phase, or we can call it angle. And how much is this phase? Well, tangent of this is b over a, so that would be tan minus 1 of b over a. Okay? For the present study on frequency response, we are not much interested in this one. We are interested in this one only. Later on, when we get to feedback, we will see that this is also important. All right, so this is the magnitude of a complex number. So how do we calculate the magnitude of this? So we see that the magnitude of h of j omega is equal to this guy. All right, so 1 is 1. So it says, take the real part and square it. Take the imaginary part and square it. And then add them up and then take the square root. When you're taking the magnitude of taking the square of the imaginary part, you must remember that the imaginary part does not include j. Okay? J is this. We are talking about b, not bj. You're not squaring bj, you're just squaring b. Okay, so what we have is r1 squared, c1 squared, omega squared, plus 1, and then the square root of that, right, according to this. So that is the magnitude of the transfer function of which circuit? This circuit here. Okay, so let's try to plot this and see what this says. All right, okay. So actually, this function is telling us something about the output amplitude when the input is a sinusoid. So let's just very generally try to plot this as a function of omega. So omega is called frequency. The unit is radians per hertz. So this is in radians per second, radians per second. Now, in some cases, we prefer to write omega as 2 pi f, in which case f is also the frequency, but that's in hertz. So f is in hertz. Okay, so these must not be confused with one another, omega and f. They differ by a factor of 2 pi. The unit here is radians per second. Sometimes we call this the radian frequency to avoid confusion with just frequency. All right, so if omega is 0, this whole thing is 1. So we are right here, 1. And as we increase omega, remember, as we increase the frequency of the input sinusoid, we're going this way, and this value becomes larger and larger, and at some point becomes comparable to 1. So this whole fraction begins to drop. So initially it doesn't change much, but then it begins to drop, right? And when omega goes to infinity, this goes to 0. So that's just the magnitude of the frequency, magnitude of the transfer function of this little circuit here. So in fact, this is what we call the frequency response. The frequency response of a circuit is this. The frequency response of a circuit is the magnitude of the transfer function when the transfer function is calculated at s equals j omega. All right, so we'll write that out shortly, but that's the basic idea. Okay, so in other words, what I want to emphasize here, that what we did in the time domain was this. Here, we applied a slow sinusoid because omega is small, right? So this is a something like this in the time domain. But here, we applied a high frequency. So in the time domain, we applied a high frequency signal, right? So all this t should go really in the middle, assuming that there's no DC here. So let's not worry about that. So that is the distinction between this region and this region. Here we are applying a low frequency. All of the low frequency is going to the output from the input. So the gain is about 1. But as we go to high frequencies, the circuit attenuates more, and then eventually we get nothing at the output. All right, so that's an example of the frequency response of a circuit. Okay, so let's move along, and I will try to summarize this discussion of frequency response so that we know exactly what to do. So, how to compute the frequency response. Okay, so in the first step, we determine the transfer function. That's something that we have seen in basic circuit theory, and of course we will see a lot more in this course as well. Okay, so that's H of S. All right. In the next step, we are assuming that the input is a sinusoid for calculating the frequency response. So replace S with j omega. All right, so now we have H of j omega. And this H of j omega is one giant complex number, right? You may have a numerator, a denominator, lots of stuff, but at the end, the denominator is a complex number, the numerator is a complex number. Okay, so in the third step, we compute the magnitude of H of j omega. So the magnitude means, for example, for the numerator, if we have a real part and imaginary part, we square the real part, we square the imaginary part, we add them together, we take the square root. And similarly for the denominator. So when we calculate this is the frequency response of the circuit. Okay, so that is the frequency response. And of course, generally we try to plot this. When we plot this, we gain a better understanding of its behavior, and then we can tell is a fast circuit, a slow circuit, and so on. All right, so okay, so let's go through this example again that I just showed you. Example. So this is a very simple circuit, but it can teach us a lot before we get into more complicated circuits. So remember, we found the transfer function for this guy, and we saw that the frequency response is given by 1 over square root of R1 squared, C1 squared, omega squared plus 1. Okay, so I will plot that again. So here's the magnitude of H as a function of frequency. Omega equals 0 gives us 1. So 1 right here, and then it starts dropping, right? Okay. So, as you might remember, we have one point or one measure of the goodness of the circuit, meaning its bandwidth. So bandwidth means the frequency range across which the input signal will go to the output. So, okay, so here definitely it goes to the output, right? Here it goes to the output. So where do I stop? So as a number, as a figure of merit, people have picked a frequency at which this magnitude drops by square root of 2, which is 3 dB. So that value is 1 over square root of 2. And we know that if you equate this to 1 over square root of 2, what appears here is 1 over R1 C1. And sometimes it's called the bandwidth of the circuit. If you want to be more precise, we call it the minus 3 dB bandwidth. Minus 3 dB means that the output is 3 dB less than the input, right? Because the gain is now 1 over square root of 2. So sometimes we call it just 3 dB bandwidth or bandwidth, but that's what it means. Okay, so why exactly does this happen? So why does the circuit attenuate at these frequencies? Okay, so here's another way to think about it. Well, what happens is that when we are here, the impedance of the capacitor is very large. Remember, the impedance of a capacitor, which is 1 over j omega, jc1 omega. If omega is very small, this is a very large number, right? So it's like an open circuit. And at very low frequencies, right around here, the circuit reduces to only this. So this cannot attenuate, so the signal just goes through, and the gain is 1. Now, as we increase the frequency, the impedance of this capacitor drops. As the impedance drops, this attenuation from here to here becomes more pronounced. So the gain begins to drop, and once we go to very high frequencies, the capacitor is like a short circuit. So if you really consider the extreme case of a short circuit, just a dead short, of course we get nothing at the output, right? Because this dead short has 0 volts on it, so the output has nothing. So around here we can approximate the capacitor by short circuit. So that's really why the circuit attenuates the signal at high frequencies. Okay, so that's pretty cool to realize. This concludes the lecture this time. I will see you next time.